I would like first of all to thank the other co-authors of this work, Professor Cornetti from Politecnico di Torino and Professor Menaghetti and Dr. Campagnolo from the University of Padua. Well, let's start from the beginning and from static fracture. So different criteria involving an internal length, a material length have been recently proposed to deal with fracture initiation of cracked and notch structures. And this framework is generally known as the theory of critical distance according to the terminology put forward by David Taylor. And we can distinguish among three different kind of approaches: stress-based approaches, energy-based approaches, and coupled stress and energy approaches. The coupled approaches are also known as finite fracture mechanics, FFM. So let us spend a few words on these kind of approaches just to give you the idea. Well, let us start from stress-based approaches. So we have a notch, and the stress field is generally a monotonically decreasing function ahead of the notch tip with the distance, with the distance, and of course, the stress field can attain finite or infinite values at the notch tip depending on the type of notch. And the most simple criterion is the point method proposed by David Taylor, and according to which failure takes place is if the stress field at a distance delta c from the notch tip equals the material tensile strength, sigma u. And there is also an average version known as line method, which considers the average stress fields and compare it with the tensile strength. Delta C here, according to both criteria, results to be a material constant since it depends on the ratio between the material fracture toughness K1C and the sigma u, the material tensile strength, squared, and this ratio is the well-known Irwin's length, LCH. Note that the expressions for the crack advance are not arbitrary, but they must be necessarily assumed if we want to get K1 equal to K1C, so linear elastic fracture mechanics. Of course, I am speaking about mode 1 loading condition for the sake of simplicity. In the case where the notch reverts to a crack. So these are stress-based approaches. And as concerns energy-based approaches, the situation is different. We consider the crack driving force function or energy release rate function, which is proportional to the stress intensity factor squared. And according to quantized fracture mechanics, QFM, failure takes place if the energy available over a crack of length delta C equals basically the fracture energy, GC. And of course, we can basically rewrite this criterion in terms of the stress intensity factor function and the material fracture toughness. Again, here delta C is a material property. Here there is this parameter, which can assume two different values depending on the type of crack, if center or edge crack, you can see here. But of course, again, it's a material property. And this value must be necessarily assumed if we want, in the case where the notch disappears, so we have a plane specimen, a plane structure, to get sigma equal to sigma u, so the classical stress criterion. Finally, we have coupled approaches, so finite fracture mechanics. In this case, we couple the two conditions. The former is a stress requirement, and in this case, we have considered the average version. And the second one is the energy balance. So finite fracture mechanics is a system of two equations in two unknowns. One is the failure stress, which is implicitly embedded in the stress field and the stress intensity factor functions. And the other one is the crack advance delta C, which results to be a structural parameter. So differently from the criteria that I showed you before, in this case it depends on the geometry under investigation. And of course, the key answer is which is the best criterion. And according to my experience, at least according if we deal with the notches or cracks, the situation changes from case to case. So it does not exist a clear, the best criterion. But of course, stress-based approaches or energy-based approaches are easier to be implemented since there is just one single equation instead of two. On the contrary, the advantages of finite fracture mechanics are related to the fact that from a physical point of view, probably it is, let me say, it's related to its physical soundness. I mean, there are people, scientists who trust the stresses. There are people, scientists who trust energy. And finite fracture mechanics basically trust both criteria, both conditions. Another advantage related to finite fracture mechanics is related to the fact that the crack advance is not a material property, so it's a structural parameter. And so this allows to describe better size effects. As a matter of fact, if you consider a simple 3-point bending specimen or on a notched specimen, W is the width, and here we plot the dimensionless failure stress as a function of the dimensional width. Of course, for large sizes, all the criteria, line method, energy method, QFM, and finite fracture mechanics provide a unit value, and this is reasonable. But when W tends to the crack advance, so for very small sizes, as it happens for some medical devices, the situation is shown. You can see the situation here. Of course, the resultant of the stress over the ligament tends to 0, Navier's relationship, and so the line method provides an infinite failure load, an infinite failure stress. Of course, the energy available, by considering also the contact point of the force, is infinite, so QFM provides basically a vanishing failure load. And FFM, so coupled approaches, are the only approaches which provide the finite values. I will not show here now the results, the comparison with some experimental results obtained by Carielou, but the agreement was satisfactory. And finally, the last advantages of coupled approaches related to more complex geometries, such as, for instance, interfacial cracks. Now, let's move to the present work. And the goal of this presentation is to generalize, to extend finite fracture mechanics to fatigue. And more in details, to investigate crack and notch sensitivity. And to this goal, we will consider two geometries. One is the well-known Griffith crack, so a crack of length 2a in an infinite tensile plate. And the second one is a circular hole with radius a, again in an infinite tensile plate. You can see here both geometries. And in the fatigue framework, we can basically, the finite fracture mechanics criterion can be recast in this way. So by introducing the plane fatigue limit and the range of the threshold value of the stress intensity factor. And again, we face a system of two equations in two unknowns. One is the fatigue limit, and the other one is the critical crack advance. So, Griffith crack, center crack, everything is rather well known. So the stress field is provided by Westergaard. The stress intensity factor, I don't know, but basically it is rather well known. We substitute these two equations into the finite fracture mechanics system, and we get this analytical relationship. Where LTH, you can see the definition there, is a sort of generalization to fatigue of the Wien's length. Surprisingly, in this case, finite fracture mechanics provide identical results to the line method, and in this case, and probably this is the only case in the finite fracture mechanics that I know, also delta C is a material constant, so it's not a function of the geometry. This is the Griffith crack, and this is circular hole. Again, here everything is rather well known. The stress field is known by, it was provided by Kirsch more than 1 century ago. The stress intensity factor can assume this shape, this expression here, where F can be found in some stress intensity factor handbooks. There is one by Tadek Paris where the accuracy is lower than 1%, so excellent. And of course, by substituting these two equations into the finite fracture mechanics system, we can get some semi-analytical relationships, which are quite long and boring, so I don't show you now. But here is the solution for what concerns the crack advance, which is, in this case, a structural parameter. It's a function of the hole radius. And here you can see basically the situation for what concerns the fatigue limit, circular hole and center crack. The gray line here is the circular hole, while the black line refers to the center crack. You can see here the two horizontal asymptotes, which govern the solution for the low and the large sizes related to the circular holes. This is one. This is the dimensionless fatigue limit. So this is 1, and this is 1/3. And this is the linear elastic fracture mechanics basically line. So according to this diagram, there exist basically 3 regions. So the first one you can see on the right is, in this case, of course, the structure is feature sensitive. The difference of a notch from a crack are relevant, and they increase with size. This is equal, I don't know why there is a square now. But basically, of course, the behavior of crack structure is full assessed by linear elastic fracture mechanics. And by considering an engineering tolerance of 5%, this is the limit according to finite fracture mechanics. So this is the first region. In the second region here, we say that the structure is shape insensitive. I mean, the strength is affected by the presence of a defect, but basically regardless its shape. So basically a notch can be treated as a crack of the same size. And again, this value was estimated basically according to finite fracture mechanics by considering an engineering tolerance of 5%. And finally, the last region here is feature insensitive. So in this case, basically the structure does not see basically any defects. So if we are here, basically no matter if there is a crack or a notch, basically the structure is insensitive to the presence of defects. And basically this diagram here can be considered as a finite fracture mechanics interpretation of the Azzori-Lazzarin diagram, which was put forward more or less 15 years ago. And then we have compared basically finite fracture mechanics prediction with some experimental data. That's the case of center cracks, and you can see also predictions according to the point method. You can see that the agreement is excellent, and probably for what concerns the geometry, finite fracture mechanics is better than the point method. While as concerns circular holes, this is the situation. Again, where there is a comparison with the point method. So in most cases, the point method results to be the most accurate. Anyway, all this data, to be honest, there are some of these data that don't refer to circular holes, but refer to notches where the stress concentration is close to 3. So the relationship that I showed you before still keep true. But what is interesting, according to what I showed you before, is that quite all the data you can see here, basically this was 1.19, the first limit, fall in the region, in the middle regions where failure is insensitive basically to the shape. So I was precise, so I implement the Kirsch relationship and so on, but if I consider this as to be cracks or V-notches, we wouldn't, you would not have observed any differences. So of course, maybe it would be interesting from an experimental point of view to have some data also here to close to the horizontal asymptote. And finally, basically what I want to show you that we have considered also surface semicircular cracks. In this case, of course, again, the stress intensity vector range can be found tabulated in the literature. The stress field, I consider this, which is a piecewise function. And again, we can substitute these two expressions to the finite fracture mechanics systems. Everything can be performed in a semi-analytical way, so quite easy. And this is the comparison with the experimental results. So in this case, I would say quite perfect. So nice. And so that's basically, I just want to tell you that this is the first step of the generalization of finite fracture mechanics in the fatigue framework. Of course, basically, there are more, the goal in the future will be to consider also other basically fatigue defects, welder joints, as well as fatigue time life of mechanical components. But so far, this is everything that, all that we have done. So thank you for your attention.
We have time for one question. Since you are talking about fatigue, did you consider, I mean, you're not referring at all about fatigue ratio. I mean, what about
yes,
fatigue
because
ratio? I mean, mean stress effect.
Yeah, because basically by considering the material properties, you can see here the plane fatigue limit and the range of the threshold value of the stress intensity factor, they depend on the ratio. So basically, I'm considering the ratio in an implicit way, let me say, because it affects basically the values of these two parameters, but not in an explicit way.
Just a curiosity, the graph that you show later on by Azzori and so on, is it the two phases of the same medal?
Yeah, exactly. Was related. That was the first basically paper. Then there were a couple of subsequent papers.
Oh. Thank you.
Okay.